Yeah, it looks great, Gary.
Okay.
All right,
Of course
Gary
it
and
does.
Adam, thank you for coming back for part 2.
Thank you for having us. Are we ready to go?
We are ready.
All right, awesome. Well, I want to welcome everybody today. Thanks for coming back for part 2. A little bit more technical abuse here with Gary Smith and Adam Robertson. We're back here with you today for part 2 of our LabScope waveform analysis discussion. And today, Adam's with me, of course, as usual. We travel as a pack these days, and we're excited to bring this to you. We do have, obviously, with a lunchtime session, a short amount of time to cover a fairly decent little subject here, and I'm hoping that we get some good questions and answers at the end. What I'm going to be going over today, guys, if you remember last session we did together at Lunch and Learn, Adam brought forward the case study with the crank and cam sensors and paying attention to the physical mechanisms behind the waveform that we're looking at. Today, I want to bring us through a recent case study on a Valvetronic motor where we had a little bit of an issue with PCM control, and the tech wasn't sure whether this was being caused by the motor itself or whether it was being caused by the driver. So I want to bring us through that case study and share with you a little bit of some of the tricks of the trade that Adam and I will use on the hotline, a diagnostic hotline, to help a shop get to a really tough answer that's not necessarily solvable via normal DTC and diagnostic routines. In other words, sometimes those diagnostic routines, guys, can get, let me say, the diagnostic routines can often allow us to out-tech ourselves, I guess is the best way for me to put that. Meaning we get so far ahead in the theory and the technology of how that system's controlled, we forget that there's basic electrical signatures and clues that are readable throughout diagnosis in these areas. Now, I think I saw Greg from Euro Auto House on here today, and Greg and the rest of the guys that are with us, thanks for joining us. But the reason I'm calling Greg out is he had a very similar, he was doing some investigation and some study on some stuff that we did in the pulse width modulation class. And I think, Greg, you'll enjoy the case study that we have here that we're going to discuss. But we're going to do it a little bit differently today. I'm going to throw a description and a picture up at you guys, and I want to kind of create a little bit of a debate from the audience on what you think could be wrong before we go flipping too many slides. And then I'm going to show you some of the ways that we could identify physically what was going on with this waveform to come to a very conclusive and successful diagnosis on the car that didn't kill the customer's wallet. So with that said, and of course, Adam, being Adam in Diagnation Control Central, he's going to be jumping in on this discussion with us today because we've run into this several times here in the last couple of months together. So I'm hoping this is going to be a good learning.
I'll show you how this works right now. You see how I just interrupted you, Gary? I'm
Yes.
pretty dang good at that part, okay? So when I do that, it's certainly not on purpose, but that one was. So
All
yeah,
right.
We'll get it going here.
Very nice. 1 second. I just got to kill all the rest of the volumes on my phone there. I just got pinged and I thought I had all my volumes down. Okay, well, with Adam's interruption out of the way, which I love when he interrupts because he's always got something good to say, let's get into it. How many times have we replaced something like an electronic throttle motor or a Valvetronic motor or something of that nature, or even a driver or a control module, only to find that the vehicle still has its intermittent fault that we were going after? Well, what we're finding, and we're going to dig into a chipset here today to show you why this is important diagnostic information. We're finding that in an overwhelming number of cases, we've got certain things going on that are creating, let's say, that Valvetronic motor to reset, or say the throttle motor in this case to reset. In this discussion, it could be any of those motors controlled by an output driver and a module. We're finding that supply from voltage side, pin tension, bad grounds, or corrosion in connectors can overwhelmingly be the cause of these faults. And we're unfortunately finding a lot of these out after good technicians have gone down a normal diagnostic path and been led to replace a modular component by the DTC chart. So this is where we get into thinking outside of the box a little bit in our diagnostics to see if we can actually track this down and get an answer. So a lot of times, many of the ghost issues that we're experiencing, especially in the case where you get a Valvetronic fault, a Vanis fault, a throttle motor fault, something that actually makes the vehicle default and drop the throttle control away from the car, or something that drastic, we're going to want to point ourselves in very certain directions. I think you're going to see as we go through this. Sometimes in the course of diagnosing these cars, we've got to really get into researching some things that the OEM doesn't share with us. For example, how does this chip work that controls this throttle motor? How does the chip work that controls the Valvetronic motor? What kinds of physical laws are in play here that can give us clues as to why this chip keeps resetting, or why this system keeps resetting? And how can we go figure that out with our testing equipment, right? So I'm going to submit to you guys that part of our diagnostics and information gathering is going to be research that goes outside of the automotive realm, right? But we also have to keep bringing, like Adam did in the last session with that waveform on the crank sensor, we have to keep bringing ourselves back to root fundamental electrical and electronic diagnosis to get the answer to that car, and get our heads completely out of the high-tech realm of the theory of the system we're working on. So let's start with this, okay? Now, what I'd like to do is, and I'm not a Zoom wizard, so I'm going to ask Brenda or Adam or somebody that knows how to control Zoom to let people unmute themselves, and let's have a coffee clatch here and discuss, talk amongst yourselves, as they say, right? I want you guys to look at the screen and understand that what we're looking at is a portion of a three-phase waveform here that controls a fuel pump, a throttle motor on a car. No, I'm sorry, a fuel pump on a car. I'm all confused. I deal with so many cars in so many cases. Now, the thing that I want to start a discussion on here is that, and let me define the waveform for you. We've got the purple trace, which is one of the three phases that is showing its voltage, and the white phase, which is turned on right now in front of us on the screen, is showing a second of the phases. The third phase in this particular case, when we were looking at voltage and current to see what our problem was here, was not hooked up, and I regret that because I wish I'd hooked it up.
Your number, Alfonso.
I'm sorry?
Okay.
Okay. Now, if we look at the white trace, that's voltage.
I'm gonna put this into my my phone, so I got.
Beautiful.
On it like a rat on a Cheeto, man. See
Thank
how
you.
fast that happens? Wham.
Yeah. So sorry. I thought he was trying to ask me a question. That's why I kept stopping. But we were actually putting a vehicle in process in the shop, and I love that. Okay. Now, the white is voltage control on this phase, and the blue is current. And the reason I said to Greg, you're going to love this, is Greg was studying this the other day. We were looking in the phase pulse width modulated three-phase class about the theory of Kirchhoff's current law, which dictates that the algebraic sum of all currents coming in and out of a single node must equal 0 amps, okay? Otherwise, we've got leakage. So what I want to do is open the floor for discussion and ask you guys to take a look at this waveform, understanding that blue is a current trace and white is the voltage trace. Take a look at this and tell me if you can see what's going on and call it out, guys. I'm going to be quiet for a minute so you guys can unmute your mics or throw some feedback in on this. What do you think is going on with this vehicle right now that's causing this problem?
gonna guess one of our other phases is not working right.
Yeah, that's a great guess, right? Because what we've got in this situation is the current clamp is around all three phases, okay? Which means
Oh,
that a
you're
side
around
of
all
the,
three. Oh,
sorry?
yeah, sorry, I didn't realize you were around all three. Yeah, that's not right. Continue.
Right. Right. We're around all three here, and because Kirchhoff's current law says we should be running around zero, which we are over here. Okay. What do you think would be causing this during the white phase operation?
Leakage.
Well, no one else is going to speak up. I'm going to say one phase is not functioning as it should.
That's absolutely right, Greg. And beyond that, if we take that Kirchhoff's current law into effect that you and I were studying the other day, and we agree that throughout this current operating range, we should be at or near zero. And when I say or near zero, the Kirchhoff's current law works beautifully in math, but in reality, as that motor or phase is cycled on and off, you've got inductive movement between the phases, which is creating slight movements off of zero, if that makes sense. However, we could agree that based on that current law, our current clamp should only be seeing those very slight variations as the phases switch, and our current should remain net zero through this whole test pretty much. Would you guys agree with that?
Absolutely,
Yeah.
I will.
Right. For example,
Me too.
on this side, right, we can see that it's pretty much net zero. And then over here, we can see it's pretty much net zero. But something starts to happen that's interesting in the purple phase. If you look at what happens with this current activity, it's not quite as bad as it is here. Okay. But we've got something going on here. Now, can anybody tell me why that is? Let's identify this, guys, right now for the purpose of this discussion as a shorted phase winding on the white phase alone. Okay. And you can see that occurring because as soon as it turns on, we get a very high current spike and the current keeps rising and rising and rising. Now, after this little ditty here, which we're going to discuss in detail, all right, notice that the current falls and it goes back to normal and it continues to work. You can't see that because the next time the white phase comes on, it's way to the right over here off the screen. This is just a screen capture, guys, right? But now, if we understand that this is representing a zero current test on the motor for leakage, it turns the phase on. We get a very high spike in current, okay, as we did over here with the purple. And then as the phase is applied, it rises and rises and rises. It does this jiggy thing and it falls. My questions are twofold for the audience. What could cause this blue activity when the purple phase is on? Okay, all this scattered current activity here. We know this is a shorted phase. My second question is, what is this activity? Any thoughts on those two questions, guys? And then we'll dive into what the answer is and how we located and identified what you're seeing on the screen. What do you guys think this blue current activity is in the purple phase that doesn't really match this one in the shorted phase? Any ideas?
Three phase. Bad diode.
Oh, that's a great guess. A bad diode. Okay, anybody else? All right. Well, let me do this. I'll do my best to explain my way through how we figured this out. Now, as to the first question, would you guys agree in any three-phase configuration, whether it's Y or delta, we're going to have, in order for commutation to occur, we're going to have one phase tied to another as they move from winding to winding. Would you guys agree with that? Okay. Now, with that in mind, what we're seeing here in the blue is that as these phases turn on and off, we have inductive energy. Okay. Let me see if I can get a quick secondary view on that. We've got an inductive energy, if you can see here, flowing through this motor. You see that, guys? Now, as inductive AC energy flows through, and we're seeing the tie between the red and the green phase right here, the tie between the yellow and the green phase right here, and back through to the red here. Okay, now it's at this point where these phases change. If I go back to my other presentation, it's at the point where these phases change and the next phase turns on that we're getting leakage from the shorted winding onto the other two windings. And this pattern repeated itself. Notice that as the inductive phase energy drops, so does the short. See that, guys? Okay, now, the next question I have for you guys is, what do you suppose, and any of you, including Adam, chip in here, what do you suppose is causing this anomaly right here? If we can assume that the leakage from one phase to the next is creating this problem, we know the shorted phase of the motor is creating this problem. What is this activity right here telling us?
Well, we can see the drops. You see the drops in current, right?
At
in
the
middle
same
right there.
time that the drops in voltage are occurring, right?
Yeah. Well, now think about this, guys. Why would the drops in current happen the same time as the drops in voltage? Think about it, you're tying the two together from the laws of electricity at that point, and they make plenty of sense. The question is, what is really happening there at that
Right.
point?
Right. Any ideas on what that is, guys? Because that almost looks like something's trying to control something, doesn't it?
Yeah,
Right.
Screen casting in the tablet.
Now let's take a look at something here. If we look, and this is the outside of the box piece I wanted to talk to you guys about today. What we're looking at here is a driver from Texas Instruments, obviously, and you'll notice up here it says automotive H-bridge motor driver. Now, these systems that are switching three-phase are using H-bridge and current pumps to provide enough energy to provide the commutation through the BDLC motor. I want everybody to pay attention to a couple of things here as we go along that will unlock for our minds exactly what's happening here. Because when I first looked at this, I said to myself, what in the heck is going on? It looks like the PCM is trying to do something here, or this motor's got some sort of chatter in it that we're reading in the form of this. But I didn't believe that, because the current just kept rising and rising. And then when this activity happened, it began to fall and fall.
Well, notice too,
Go ahead.
Gary, go back to that picture real quick.
Sure.
It's kind of interesting that happened at the peak portion of the unequalized current on the blue trace. And think about this, guys. You know, you said something that really got my attention here, Gary, because I'm not quite sure what's going on yet. You know, you've got me on the spot with this, which is awesome. I love this. But when I look at the way you're explaining it, why would we have that control, because I'm going to call it control at this point, at the peak of when that current hit? It's almost like that current hit a particular spot, and the module or somebody said, hey, whoa, time out. We gotta take control of this situation, because this is a very a very timed event to me, Gary. It is very timed.
It is. And you know what? In full disclosure, Adam and I did not look at this case study together before this event. So what I'm going to say to Adam is that is a super duper good read on what's going on here, Adam, because this that I'm circling right here, where it's got the sawtooth activity in the voltage and in the current waveform, is exactly what you think it is. It is the chip that's hitting a certain level of threshold on current, and it's going, wait, this is not right, and it's going to take out the driver.
So
Okay.
Gary, don't you think for a minute here? I loved what you said. So you brought up the limit. You brought up the current limit. Wait. But temperatures do that too. All right.
You bet.
And so there's a couple things to think about there as far as the chip interaction. That's pretty cool.
Right. Now, here's what's neat about researching technical problems outside the box. In other words, look, we know that when you get a picture of an ECM or a DME module in the wiring schematic, it does not draw the internal circuitry. Would everybody agree with that? Which is why understanding signatures intelligence on your waveforms, this is a signature intelligence issue. Okay. If we understand electronic signals intelligence and we can relate it to what's stated on this chip sheet, what you'll find is the exact answer to what's going on with this car. And that's one of the things that I really love about researching tough cases that folks aren't figuring out, because there is an answer to everything we're seeing on the screen. And what I'm finding, guys, and I'm sure you are too, is that it almost always comes back to a basic electrical fundamental and not to a high-tech problem. Now let's follow this through. If we look at the bottom of the left side here, and I don't know how big this looks on your screen, but I'm circling an area that says protection features. And the first thing it says is voltage VM, which is voltage into the chip, under voltage lockout. The next thing down it says is under voltage charge pump, which is the capacitors that charge up that circuit and hold the voltage up high so that when the motor switches phases, it doesn't dip the voltage down. So that charge pump is providing voltage regulation to the pulse width modulation as it is cycling through the three phases, right? The third thing, which I'm not sure I captured, let me see if it is here. Let me just read this to you because this becomes very critical. Fourth paragraph down. In addition to the high level of driver integration, and by the way, guys, when we're thinking about what we learn in our training classes, which is you've got a microprocessor that's outputting a TTL signal to a transistor wired onto the board to fire that motor. In this case, we would be incorrect. Technology has moved us to the point where the chip itself has the MOSFET driver built into the integrated chip package, and the output that's controlling that motor is the chip in this case. So listen to this statement because it unlocks what's wrong here. In addition to the high level of driver integration into the chip, the device provides a broad range of integrated protection features. These features include power supply under voltage lockout. Let me stop right there. How many times, I asked in the very first opening right here, how many times have we replaced that throttle motor only to find it come back in on the hook defaulted? And yet, when we get it off the hook, guys, what happens almost every single time with throttle motors? We go out to the vehicle, we key it up, it comes alive and drives right into the shop with no problems, okay? This is important. That's under voltage lockout. So it is really, really, really important, since a lot of these cars will not set under voltage codes from, let's say, a battery that's falling down a little bit when it's on initial crank in cold weather. And we're going to get that throttle motor or that Valvetronic lockout right as soon as we start the car, because the battery dipped down to 8 volts and then came right back up to charging system And of course the car runs, but now guess what we've got? We've got a chip protection strategy in here that defaults the throttle motor, and now it gets towed into the shop. You want to know why it keys up when it's fine? Listen to this. Okay, we have under voltage lockout, we have charge pump under voltage lockout, and look at this. We have over current faults, open load detection. Why would, guys, why on an inductive motor would a chip provide open load detection? Any ideas on that? Talking about physical electricity in motor circuits. Because
Gonna
just
guess
like with,
they-
go ahead, please.
To save itself?
That's exactly right. Okay, that when we talk about these protection strategies, it does an immediate save itself, doesn't it, Greg? Because what we know about inductive energy is if it is sent out on a primary circuit and it has nowhere to go, guess what it does? It reflects back to the source that created it in the form of heat on the junction of that transistor, and it slowly but surely, or sometimes quickly, works on that driver and just takes it out. So overcurrent, overcurrent will shut it down very quickly for the obvious reasons that we see on the screen for protection, like Greg said, but also open load detection will do the same thing. And guess what? Under voltage, guys, will do the same thing. Okay, so while these DTC charts have us focused on disconnect these two sensors and ohm the wires between here and here and this and that, and we're spending 3 hours testing down this trouble chart for this throttle motor code or this Valvetronic motor code, we're being fooled and run around the process the whole time, because what the manufacturer is not telling us is what happens next. Okay, any kind of output short the battery or short the ground is also protected, and thermal shutdown is protected. Like Adam said, didn't Adam mention, hey, a lot of times these things will happen because of heat, right? The device faults are indicated by the end fault pin, and this is chip language, but follow me through it, with detailed information available in the device registers. Now, let me stop you right there and tell you what's going to go on with this thing. All the data sheets that will give you information on these default activities will also show you waveforms of what will happen when that default activity takes place. In this case, in this particular case, and this data sheet does not match this car, by the way, I want to be clear about that. What I'm pointing you guys in is a diagnostic direction here to understand what's going on. In most of these scope waveforms, they'll be tied on the data sheet to one of the protection lockouts. For here, you can see this is overcurrent protection. Look what it does to the driver. It shuts it off. But what's going to happen here, and I wish I'd have taken this picture one set down, is this is going to set about a trip, a motor trip and protection strategy, if you will. Let me see if I can get this up out of my way. Yeah. Okay. And when this thing goes to reset, it is going to, I was hoping I might actually have messed up and not gotten this captured the way I wanted to. Hold on one second. Okay, it's not captured here, but let me paraphrase this to say this. When we are looking at a data sheet and we have these functions, this tells us what's going on, because here's what I found out on this particular problem via that description. When an overcurrent or under voltage occurs, and in this case, it's gonna look at that as both, okay, because it's going under voltage here and it's going overcurrent here at the same time. So this motor driver is immediately shutting off. What I found out about this from reading the data sheet description is that when that under voltage or any of those four faults occur, under voltage, undercurrent, over voltage, overcurrent, or the temp faults, this will go into a default. When it drops the throttle motor out from under your foot, for example, the very next thing it does is tries to reboot itself. That's the activity that we're seeing here. And what it does is it reboots and it looks for 500 microseconds for these same readings. And if it sees it, it dumps it out again, and it rapidly tries that. And it says it in the data sheet, guys, and this is why I got excited to show this to you today. It drops it out 5 times, and then it shuts the driver off after the 5th check and sets the fault. Look at what we have here. 1,
Hold on.
2,
Before you go any further, Gary.
4, 5.
So let me bring something up. You've got the 5 dropouts right there. That's pretty
And
cool.
that's
And it
the
meets
chip trying
everything.
to reset.
That's right.
Right.
But now let's wheel this back for a little bit and look at me from a technician standpoint. This vehicle, and I don't know anything about this vehicle. This is wicked cool to me, by the way. I don't know anything about this vehicle, but my gut tells me that this diagnostic software in this PCM, this module, may not be programmed or smart enough to say, hey, we tried 5 different times, man, and we couldn't get it to come to life. He didn't say possibly under voltage or overcurrent. They might have left that part out. What they may have just told us, guys, is this: hey, my APP and my I'll just use an accelerator pedal as an example, because they leave you freaking stranded when they go wrong. So here you've got a car that may have simply said, wow, I commanded my motor to move X amount. I didn't receive it from feedback from my throttle position now. So his only diagnostic code strategy, which is the possibility here, his only code strategy may just be able to say, hey, I commanded it, but I didn't see it. My TPS1 didn't equal my TPS2. I didn't get the response I wanted. Instead of, which would have been neat, instead of the dude going, hey, by the way, we had an under voltage situation. We went into chip protection. We tried it 5 freaking times, couldn't recover. We shut it down.
Right.
That's pretty neat, because the codes alone and the troubleshoot code charts can be so misleading because they are not going to show you this.
Right. You know what the code was? The code was motor mechanically faulty. And it was reading that because of this, but it never identified whether it was overcurrent. Like you said, it never identified whether I was overcurrent, under voltage. Now look, some of the newer cars, as we know, are perfectly capable of calling out that individual circuit in the case of the extensions on the OBD2 codes. For example, P0136-87, that's a power circuit fault, right? Okay. Well, maybe if this was a 2019 car, we would have gotten that kind of indication out of it to point us right into the motor circuit. In this case, we didn't have the technology in this car for the computer to figure that out on its own. And we had to go in and diagnose what was going wrong with this thing, because quite frankly, we didn't know if the motor was causing it, the driver, a shorted wire, or what. But when we saw this, like your mind told you right away, Adam, that is too logically based looking to ignore that. Something's going on with this PCM that's throwing it into either a reset mode or a try it again mode. And lo and behold, when we looked at the data sheet, what I'm trying to get across to the techs that are on with me today is that the manufacturer and all data, and sometimes even Google, are not your only resources. I mean, Google was a resource in this case because we looked up the data sheet on it. But my goodness, guys, the amount of diagnostic information to explain the physical mechanisms that we're seeing going on the screen here, to me, are overly exciting, because now that just broadens my knowledge of signal processing and what's going on with that chip. It's one thing to understand the in waveform and the out waveform to try to analyze on the screen. Okay, I can see we got a bad motor or a bad something going on here, but what is it and why? And when we can put that physical connection with the information in the chip in detail, like you see on the screen, okay? I mean, this even tells you how the chip is set up. Okay, with the tick-tock of the capacitors and resistors and inductors that make the pulse width modulation drive this motor. That is where we can make a connection. If we think about the dude in the box there, or the Herm in the box, right? And we think of him as an empty head and an empty drawing and a schematic that has no information for us technicians inside of it. Guess what we just did with this data sheet? We took the input and directly connected it with the output and a fault that we saw on the screen and we were able to physically explain it and make the right call on the car, because the call on this car from the shop that was working on it was to replace all three. Okay. And there was nothing wrong with this driver whatsoever before or after the repair. Now, if the guy had kept driving it along like this, I guarantee it would have smoked the driver out of it. But in this case, a motor fixed it, and it didn't need a DME, and it didn't need an eccentric shaft and a sensor, and it didn't need all the other stuff. It didn't need a throttle motor, and it didn't need this, and it didn't need that. And that's the important piece of the discussion we're having today, is the physical ID on the problem, guys. Go ahead,
So
Adam.
cool about this, what you just said, and I'm going to reiterate it because this is awesome to me. So you said, Adam, it did not have a problem with the driver yet. Did not have a problem yet. Okay. It had a mechanical, or I should say an electrical fault inside the motor itself. Okay. But by looking at this, you guys should be able to look right out there and say, Adam, I really doubt there's a driver problem with this, because now that we looked at the data sheet was a key here, Gary. I love it because, from a technician standpoint, working on cars every day and filling dump trucks with parts we didn't need to replace and all the things every one of us has done.
Sure.
It's the data sheet that took the magic of the box and opened it up and said, look, right here, right in the blue trace, you watch that drop, the drop of current, the touch. It's like, I kind of explain it sometimes like touching a hot stove. The stove is hot,
Ouch,
but no,
ouch, ouch.
what do you, ouch, ouch, ouch. And a couple times you're okie dokie, but you touch
Right.
it too many times and, well, you were stupid. Okay.
Well, right.
But so in this case right here, having the data sheet, finding the data sheet, looking at the fault recognition and the fault response shows you that driver, everything involved, the logic, the driver, the whole thing is doing exactly what it's supposed to do.
Right.
When it did it, for the time it's supposed to do it, everything. And
Right.
that should be a clue that not only is the driver and the logic doing its job, you don't want to even think about replacing it yet, because you might put in a broken freaking part and really put you into the tailspin, the rabbit hole that we find ourselves in.
Well,
It's just-
that's a great point, right? Because even if we weren't dealing with first of all, I was psyched, and I mean psyched obviously we caught the problem on the screen here. I just had to explain it, if that makes sense. And believe me, I almost melted out of my chair, guys, when I opened up that sheet and looked at what the default strategy was for the chip in an overcurrent condition. 5 reset attempts in 500 milliseconds, and then it shuts off and it defaults, and it won't let it start again until it's repaired or cleared. Okay. Now, if that does not connect the dots to all that ethereal information in that box that the OEM never gives us to make these diagnostic calls, I don't know what does. Because let's look at this. And then we're going to open it up for some discussion before we end. We're in good shape for time. Okay, but look at this here before let's assume it wasn't a shorted motor. Look at the stuff that can happen inside of this, which makes it really interesting to go look at the physical signatures on waveforms and find out how they were electrically derived. Because just what if, instead of a shorted motor, we had a power supply problem on that chip? Okay, and it's telling us that it's taking into consideration parasitic wire inductance between the power supply and the motor driver, and it's showing us that we have a bulk capacitor so that the motor voltage doesn't drop, and this IC bypass capacitor. What is that? That is to remove DC from those lines and leave the information pure. Okay, now, if I had that part of the chipset failing in the power supply, my question is, if I understood the physical functions of a capacitor discharge that was going rogue, would I have caught it on this screen, Adam? Yes or no?
You would have caught it.
You bet you would have
Absolutely.
caught it.
Yeah.
But unless you study the fundamentals of electrical activity, guys, and how it looks on a screen, the behavior of that voltage and current, you'll never catch that fault. That's
I was
my
just
point.
going to say, yeah, you'd see it on the screen, but unless you recognized what that signature was, you wouldn't recognize it as what it was doing.
Right.
Ah, that's cool.
Now, now to close this discussion up today
Wow.
on the importance of understanding the physical waveforms on that screen, here is the zoom of that fault caught a second time so you can see the single phase doing the reset. Okay. And to me, when you can put a signal set in the information and answers together like this, believe me, this was a tough diagnostic case that sat at this shop for a number of weeks before it was figured out. And everybody was trepidatious to figure it out because it was a BMW and the cost of repairing the car with the, bright red parts cannon barrel, approach of just do all three. That would have been, Greg, you could tell me better because you work on these things all day, but on an older 7 Series car like this, I've got to think you're going to spend $6,000 or $7,000 in parts and labor chucking all that at the car. So I'll shut my mouth in a minute and let Adam have his closing remarks. But what I want to say to you guys is I want to open the mics and I want to have a discussion about how important you guys think, understanding the physical mechanisms of what's going on in your scope screen are, because there is nothing advanced going on here. Once we have the data sheet that says, here's what the PCM is going to do with this fault, there is no mystery on this screen whatsoever anymore. Would you guys agree?
Wow.
Adam, what's your
Well,
thoughts?
I'll tell you exactly what my thoughts are. And this goes back to part 1 of this series last month, Gary, when we were doing this. And one of the points that I tried to put out in our first introduction to this is being able to compare a known good waveform to a presumably good, a presumably bad. Is that really enough? And the answer is no. It is not enough to be able to say, hey, I got a good, hey, I got a bad. Because honestly, Gary, this is speaking right truly for me. Without the explanation that you just went through in the measly 45 minutes it took, which you look at the big scheme of things, Gary, you look at the study time that we use when we have a problem car. When you say, hey, turning wrenches is one thing, collecting the data, sitting down and study and looking at those data sheets and going through everything, that time may feel from a flat rate standpoint like it's wasted, but in the reality of it, it's everything in diagnostics. And here's where I was headed with this. Looking at the original waveform, Gary, when you put that up, I was looking at it and I'm like, interesting. A couple thoughts went through my head. I either have a control problem or a shorted winding problem. That's what Adam was sitting here thinking. I've never seen this waveform before. So I'm going, wow, I either have, now catch this, Gary, and all you listening, of course, I'm talking straight to you here, but here's the thing. I looked at it and said, control problem or a motor. Gee, what do we do? Fire up the parts cannon? Because
that's what we were facing. Exactly.
Well, I got to admit, until you pulled out the data sheet and we explained this, I would have been more inclined to go with the computer. Seriously.
And that's the beauty of this session, guys, is that, this is how, no matter how involved you are in diagnostics, this is how we as technicians can get misled by OEM service information and DTC test charts, because this problem was there's no way that I shouldn't say there's no way. I'm not trying to be arrogant or in any way when I say this. Believe me, most of you that know me know I'm a humble mechanic like you guys are. But what I am going to say is, because the study wasn't put into the car, nobody could fix it. That's the most, that nobody that had this car was fixing it. Let's put it that way, guys.
Well, let's do something else there, Gary. If I had a known good waveform, see, this is where my lizard brain thinks. The first thing that most guys want to do
is a lizard brain, I might add.
I trust me, it really is. So here's the thing. The first thing most of us want to do, and I'm guilty of it, is I'm like, hey, does anybody have a known good waveform of that? Well, first of all, ain't nobody going to have a known good waveform. But even if they did, think about this, guys. Even if they did have a known good waveform, said, hey, Adam, here's a known good waveform. So I've got a known good in this hand. I got mine here. I would still look at it and go, well, something's wrong. I'm smart enough to do that. I can look at it and say, hey, these things don't look the same. But I honestly think without your demonstration, Gary, and explaining the diagnostic direction used to dissect this, if that portion was not used, if we didn't think outside the box to look inside the box, for lack of a better statement,
right?
I don't think,
good way to put it.
Well, but I don't think the right decisions would have been made. And here's what I got out of you today, Gary. And I'm not cutting everyone else if you have something to say. Here's what I got out of this. I don't care what car this is. I don't care if this was a BMW. I don't care if it's a throttle motor on a GMC truck that leaves you in freaking tennis shoe mode on the side of the road. I don't care. But most of us within the sound of our voice has been through situations where something which should seemingly be as simple, there's a simple word, as a shorted phase could be completely misconstrued because of, gosh,
There's a lack of information from the OEM.
there's nothing there. There's a box. It shows a couple wires going in, dude. All right. We've been there. The thing is, I honestly think that this is a situation where a lot of guys would rather be lucky than good. And they say, well, let's put a motor in it first. Boom, we hit it. Have no freaking clue why it did it.
Yes. And
you see what I'm saying?
And guess what, guys? We have in our careers, all of us, if we're intellectually honest, fix cars that way. The really exciting thing about what we're doing with these lunch and learns and the trainings, and Adam and I getting our heads together on these deep study cars, is that we're learning too. And we're trying to bring the aha moments of solving these cases on the hotline to you guys, and what I call seat of the pants diagnostics. Here we go. Here's a car we were stuck on. Here's an answer we don't have. Let's go find the answer. And to me, guys, to have figured out this right down to the data sheet describing exactly how it's going to happen and how many milliseconds it's going to be before it shuts the phase off, I got shivers up my spine. I was like, oh, this is unbelievable, man. Why can't the manufacturer just give us this little bit more information and we could have tied this all together? But anyway, so guys, Adam and I'll shut up for a minute. Do any of you guys want to unmute your mics and shout out and make any comments or ask any questions before we have to go back to work?
Yeah, my initial look at that waveform would have told me, at least in my mind, without the data sheet, that was a winding issue.
Right, which is really good that you're able to identify that. That means you study already, right?
Yeah.
The neat thing is this test that we're doing on this screen is, unless you are a student of some more advanced thought process with testing, you're not going to catch this because your current probe is around one of the phase wires, not all three, and you're not looking at Kirchhoff's current law to catch that.
Exactly.
Right. So that's the beauty of us getting together and sharing these testing ideas. Like, for example, why can't BMW say, use Kirchhoff's current law, put a clamp around all three and look for leakage? I mean, how hard was this? Once we really understood what was going on, how hard was it to catch it like this? It was easy.
By the way, I'm going to throw just another small piece of technical comment out here. If you go back to that, Gary, if you go back to that waveform right there, one of the things that you brought up was, if we use Kirchhoff's law and we're around all three phases, that it should be zero-ish, not zero, zero-ish. Guys, you also need to understand that there's a thing that some of us refer to as flyback. And what we're talking about is, you've spent all this time building a magnetic field to produce something. Energy cannot be created nor destroyed. And so as you see that lack of zero and we go, oh yeah, hey, that's acceptable because yada, yada, yada. Well, understand that some of that's flyback from the other circuits being shut off. Do you realize that some of the logics are built today in our threes, our brushless motors, that they can use the amount and speed of the feedback as RPM indicators on how fast the actual motor spinning. So
Yep.
what we see is a useless detail, completely useless. Hey, we just accept that, man. It's useless. We could teach the little dude in the dash to say, hey, we know this is part of the law. And as we see the speed of that come back, that's giving us our speed indicator. Instead of having to put a Hall effect switch on it or truly measure speed, they can really say, hey, we're 2,000, 3,000, 4,000, 5,000. And it was just software rather than extra hardware to put
Yeah.
that speed indicator on that electric water pump or that
Isn't
fuel
that
pump or
cool?
that. It's just cool to me. It's cool.
So just what Adam was saying about the flyback, if you want to quantify that on the screen here you've got flyback under control. Here you do not. Notice these spikes coming way down when this current is jacking way up. This is your voltage representation of your flyback occurring against the ground of that driver right there. You can see it in physical form right there. See that?
I might just add one thing to this.
Sure.
Being I just dealt with the one you were talking about earlier, Gary.
Yep.
I expected with my amp clamp around just one of the phase wires to the fuel pump, and this is a 3-phase pump controlled by a fuel pump controller.
Yep.
I expected to see somewhat of a sine wave. Not at
Yes.
all. Things got a funky step as it comes up, and then another step as it comes down.
Right.
Apparently because of the chip design and the way it turns on and off.
Yeah, specifically, Greg, that's a function of the H bridge, okay?
Exactly.
Which is the driver chip. But in the case of an H bridge, when it's driving AC or when it's driving inductive AC in a BDLC, I should say, the flip-flop, okay, is the flip-flop between above the ground line and below the ground line becomes the issue, which is why you didn't see what you expected to see.
Well, I'm going to throw in my 2 cents and say, Carrie, that was friggin' awesome. I loved it. That was just incredible. And it was a great explanation of how, like I said, we thought outside the box to see inside the box. And, if you guys seriously sit back and think about the minuscule lesson that was put out there today of all the different circuits that we can apply that to, and the honest, true value of what understanding what the squiggly lines on the scope are telling you. It is there. We just need to be able to interpret what those lines mean. And frankly, comparing a known good to a known bad is not enough. It's just not enough.
No, that's right. All right. Well, anybody got any other comments or questions? All right.
Well, likewise, Gary, this was awesome. I don't know how many techs are going to be pulling up data sheets on their drivers and figuring out what's going on. That might be a little beyond where a lot of us are at, but just understanding when you see something funky like that, you have the ability to figure it out that way is just awesome. So thank you.
Well, thank you, Greg. And I didn't want to drive this to an over technical level either, but I found this to be, once it was explained in the data sheet and we could quantify it to what was on the screen, I'm like, I said to myself, my goodness, this is as basic as it gets. But when I first started looking at the waveform, it wasn't basic and I couldn't explain it. And that's the whole point of understanding measurement and signatures analysis. The signatures meaning what is coming out of the PCM and why is it coming out of the PCM that way. So yes, I agree. Not a lot of guys are gonna, we had one comment that said, this is why we have our successes after we replace the parts. And I think it was Kenneth and Maggie's team over there. And, because quite frankly, this car took a lot of study time to figure out, but it was the difference between getting it right in a $2,000 repair versus an $8,000 scatter repair. And I'm sure that even though the customer might have spent the $8,000 and got the car fixed, I'm sure he and the tech working on it we're grateful for being able to figure it out and actually diagnose it right the first time. So yeah, so thank you guys on that.
Yep.
And if nothing else, Gary, next time I see that pattern on a three-phase, I'm going to immediately think back to this class. So
I'm gonna know what it is. Yep. All right. Cool. Anybody got anything else they'd like to go over before we end this today?
Yeah, is my mic working?
Yes,
It is. It
Okay,
is.
great. Hey, Gary, it's Jeff Damshin here at Bainbridge Island Modern Collision.
Hey,
So,
Jeff.
hey, how's it going? Looking forward to seeing you guys here in another month up here at ATE, so that'll be
Yeah.
fun.
It is gonna be fun.
Question about this waveform. So
Yep.
when this does this 5 thing, it then shuts that off. So this isn't going to work after that. So if you were to look further in this waveform, the white phase is off, or does it completely shut off all 3 phases?
Shuts the whole thing off after maybe another second or two out to the right. It shuts the whole thing down.
Shuts the whole thing down. Okay, that's what I was wondering. So no, that's super useful, and that's kind of, I don't know why it shows as KA for my thing there, but that was my comment about always trying to find that smoking gun, and this is the kind of stuff that helps us do that. So we're not doing the parts cannon, and we can hit it right the first time. So I always love your teaching, and very much appreciative of all the knowledge that you guys have and being willing to share it with us all.
Well, thank you guys very much. I appreciate that. It's a nice compliment. All right. So.
You know, some of the archive. Hey, Gary.
Sure. Go ahead.
I just asked him to unmute.
Did you archive the first one of this series?
Brenda, I think Brenda would have to answer that question because that's all controlled on their end. Did you guys archive that last series, Brenda, in the form of a recording?
No, we had a newbie person and they forgot to hit record. So do you
so
want to
I have to
do it again?
I guess we'll have to do it again, Brenda.
I was gonna say we could do it again and just put part 1 after part 2. You up for that, buddy?
Yeah.
Okay.
Why not?
That'd be great.
As long as it's after April, whenever we get back from ATE, I'm good with it. If I have one more thing on my plate between now and then, I think I'm going to keel over, and I don't want that either.
Oh man, it is definitely the convention march.
It's
Yeah.
incredible busy. Like as we sit here and talk, the support line's going ding, 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 ding. So
No, we'll schedule you in for part 1 in April. That would be great.
yeah,
That'd be
that'll work out great.
fantastic.
Yep.
Yeah.
All right, guys. Well, listen, we're going to jump. We're getting into critical mass here on the hotline, and I'm sure you guys got to get back to work. So Brenda, if we can go ahead and end this, if you